Writing code with AI takes 30 seconds, but reviewing it takes 45 minutes. If you feel like you've traded actual building software for babysitting 500-line pull requests, you are paying the AI verification tax. What if you can engineer an inner and outer loop that could automatically evaluate code intent and the integration rules before you even touch the diff? I'm Derick Chen, and this is BuildWithDC. As a senior AI development engineer at Google, I build autonomous AI systems for enterprise workflows. Before this, at AWS, I led the AI-driven development lifecycle program, or AIDLC, across APJ, helping teams scale delivery velocity without sacrificing software robustness. In modern spec-driven development, whether you follow the formal AIDLC or other specification frameworks, code generation is no longer the bottleneck. The real friction has shifted downstream to the verification of engineering outputs. When teams first adopt AI-driven development workflows, they all struggle with the amount of human verification and usually fall into one of two extremes. The first extreme is the unit test fallacy. Teams generate hundreds of unit tests alongside AI code and assume that 100% test coverage means that the feature is ready. In the early days when LLMs were not as robust, AI took crazy shortcuts when you were not watching to simply change the unit tests for the failing test cases instead of actually fixing the implementation. But recently, as LLMs got smarter, generating unit tests that pass local syntax and isolated runtime logic becomes trivial. However, unit tests only verify isolated local correctness. They fail to catch architectural drift, broken system integration, or missed business intent. Unit tests can no longer be the primary pillar of your test strategy, especially when you are working on a brownfield application. The very other extreme is manual bottleneck. Frameworks like AIDLC are a massive step up from unstructured vibe coding because they replace ad hoc prompting with rigorous application context and structured specification with incremental context building. But because AIDLC enables models to generate entire features and larger multi-file codebases in minutes, it inadvertently creates far larger scopes of verification tasks. Senior developers still end up spending 80% of their time performing exhaustive, line-by-line manual code audits on massive diffs. Or sometimes, less technical builders will simply blindly accept everything and ship to production. You will end up spending more time verifying and fixing code than you ever saved writing it. That brings us to the future: dual loop automated verification. And to put it simply, your inner loop restricts what an AI agent can do while generating code, while your outer loop evaluates what it actually built after the pull request is opened. Smarter models do not need more unit tests. They need automated integration and intent verification, as they take on larger units of work and consume more tokens in the context window. Think of a traditional unit testing like checking whether a single bolt fits into a single nut in the factory. Dual loop verification is like an automated laser scanner on an assembly line that can continuously check whether the overall engine block fulfills the structural engineering specification. So let's look at how to actually build this dual loop setup in practice, using a travel booking engine service as our codebase. This codebase was created as part of my full AIDLC demo using Claude. I'll leave a link above if you're interested. The inner loop handles real-time execution bounding. The most practical features in most modern agentic development tools, including Claude, are skills and hooks. A skill is model guidance, loaded dynamically when needed. It teaches the agent conventions, context, and preferred repository patterns. Whereas a hook is a deterministic system enforcement, a hard shell intercepting tool triggered based on rules. Skill is activated conditionally by the agent at inference time, and hook is triggered after changes are made by Claude. Let me show you how this works together to accelerate your inner loop verification. So I created a skill to enforce security considerations in Claude deployments. By declaring when to use the skill, Claude understands when to utilize this skill in a session, instead of loading this into its context all the time. You will see that it gets triggered even on a different task that intends to increase the throughput level of the system. While Claude is tasked to scale up Fargate and Redis instances by changing the design document and the Terraform template, The hook gets triggered after the write operation and highlights the security violations that Claude must fix. The hook is configured to trigger after tool use, so it runs a deterministic validator script on the infra design document and the Terraform scripts. This is an example of frictionless guardrails you can build and release to the entire engineering organization to shift left verification and to reduce human review fatigue. While the inner loop hooks keep the coding agent in bounds during the generation phase, you still need to verify the output intent before human review. That is where the outer loop semantics verification stage comes in. Semantic verification means evaluating whether the code implementation matches the original product and the architectural requirements. This is necessary because skills are loaded conditionally and dynamically by Claude. So if for any reason the specific skill and hooks were not triggered during the implementation time, we still have a chance to catch the issue here. To build this stage, you first abstract your application knowledge into two contextual resources. Product context, containing user stories and acceptance specs, and implementation context, containing the architectural decision records and module boundary rules. If you follow a structured context workflow like AIDLC, all these contextual documents will already be available. I've made another video to explain the scalable way to architect specifications for complex systems, so check out the link above. And then we build an evaluator agent. But there's a catch here. Garbage in means garbage gets evaluated. If your product specs are just 3 vague bullet points in a Jira ticket, your evaluator agent has no baseline for truth and will rubber stamp hallucinations. Outer loop verification forces your team to write rigorous, machine-readable specifications. And next, you integrate the isolated evaluator agent into your CI pipeline using triggers like GitHub Actions. When an AI coding agent opens a pull request, the CI pipeline triggers this independent evaluator agent. It's very important that this agent runs in a clean context completely separate from the coding agent in order to eliminate bias. The evaluator agent ingests the Git diff, pulls the product specs, and compares the implementation against your architectural rules. If the coding agent introduced a direct database call inside the presentation layer or ignored an edge case specified in the PRD, the semantic evaluator flags the structural violation immediately and posts a detailed report directly in the pull request thread. So how much time is your team currently losing to manual code reviews every week, and could be saved using a mechanism like this? Now let's talk about the real engineering trade-offs and limitations of building agentic evaluations. Semantic verification in CI is not a free silver bullet. First, running LLM-based evaluation agents adds minutes of latency and token costs to every pipeline build. Second, you run into the model coupling trap. Your evaluating guardrails and agent prompts are usually highly optimized for the specific AI model and the tool you're using today. So when you do decide to upgrade your foundation model, say from Claude 5 to a newer version, the model's underlying reasoning behavior might change. This means that a simple version bump possibly requires you to rewrite, retest, and update your entire evaluation harness. You must treat your evaluation prompts and context files with the exact same version control rigor and regression testing as your production source code. And finally, there is the meta review problem. If an AI writes the code and if an AI reviews the code, who is watching the AI? Your senior engineers do not stop reviewing entirely. Instead, their job shifts to the audit loop. They randomly sample maybe 1 out of 10 pull requests to audit the evaluator agent's grading logic, ensure that the outer loop hasn't silently drifted. And initially, you will definitely spend more time in the IDE doing manual reviews once you adopt an agentic SDLC process. This is daunting and tiring. I've been there too many times myself. But eventually, your organization should have a central team that governs and releases the best practices and guardrails that will be applied into the inner and outer loop, making manual verification very minimal. So to wrap up, traditional unit tests prove local syntax but fail to verify integration and intent. In the inner loop, hooks provide deterministic enforcement while skills guide the model reasoning. In the outer loop, abstracting application context into CI-driven evaluator agents eliminate up to 80% of the manual verification tasks, but requires rigorous specifications and continuous harness maintenance. If you like my content, Remember to like the video and subscribe to the channel. My name is Derick Chen, and this is BuildWithDC. See you in the next video.